Hello, everybody. Let's get started. 7:30. We have some participant already. So our topic tonight was this second part of the cache memory, and there is mainly like we're trying to see how the cache memory operates um, and those kind of stuff. Is there any specific question from any of you on that topic? Let me see if there is anything on the discussion as well. No, there is nothing on the discussion side. So, okay, all right, let's get started on then. So let's start with this overall conception, give you the overall conception, how that operation happens on the cache memory side. So if you go to the whiteboard of this class, you'll see there are like two things. One thing is the memory. So this is residing outside of the processor on the motherboard, this component. And the other one is the cache memory. This is actually within the processor. Like within the processor chip, this cache memory resides there, which is faster access than the main memory. And the main memory is equally divided into M parts. Each of them are k words long, let's say. Let's say each of them are k word long. And we have, let's say, okay. Okay, we have this keyword, and let's assume this k is somewhat power of 2. Okay, so it is a, if you do a log base 2 of the k, you get an integral number. So let's assume that, because that actually helps us, those assumptions, that these numbers like the k and number of cache lines c, those are power of 2, help us to, yeah, cache money, yeah. So those help us to avoid the division circuitry, these, we need to do mod operation, div operation on those. But if we assume it is a power of 2 values on k and c, then we can avoid the uh, those extra circuitry to compute specifically for division and modulus result. So we have a couple of definitions in this scenario. Before we go there, what I want to also discuss is this part, that pictorially it sometimes it can be a little bit confusing, means what is that block is, what is this whole block is. This is kind of a very like thin line we draw, but this whole line contains k number of words. Okay, let's say this is a k word block. So k number of word, let's say the entire block, that is a let's say its block size is let's say 4k word, 4k word. And then this guy has 4k of them, like word 1, word 2, word 3, like that. It has the entire 4k number of word situation there. So this is the entire block we are talking about. It is not just a one string, one length, one word or two word. It is the entire block with the k words are copied into one single cache line. Okay, so it is called a line, but it's really storing an entire block. Then then we have, if we have that concept clear, we have this couple of other term that is being used. One is the it's called a block address. Block address. Let's call it BA. So block address is that which block we are talking of. This, if you, the question is size of block is specified by the system. Yes, size of block is predefined by the hardware, like the cache it has. They define, okay, this is my block size. Okay, so this is very much predefined. So anyway, this block address is these numbers like block 0, block 1, or block 2, block 10, block 15, those 1, 2, 3, 15, etc. These are the, we call it a block address. And this is determined using given an address A to a div with respect to K. So this is the block address. Now there is another term called block index. Block index. Let's call it BI, which is A mod K. Okay. So what is a block index in concept? Let's say you want to, given block, in the block 0, you want to access this specific word, let's say middle somewhere, right? So this block is consist of k word, like word 0, word 1, word 2, till word k minus 1, right? So what is that index? Let's say you are trying to access word 2, that index. So that's your block index, the index within the block at which your target data, you are targeting to access that data. So that's the block index, and which is calculated by A mod of K. Then from there it comes to this definition where we assume, okay, for our first assumption is K is somewhat like 2 to the power I in that form. Okay, and here we have C number of cache line, and our assumption here C is also 2 to the power some number, like maybe J. Okay, so what is the question we have? So if the memory is word addressable, is the block then the size of one word, or how do we know its size of it? It will be given in the problem. Okay, if it is an word addressable or byte addressable, let's discuss with respect to the word addressable, but byte addressable, for byte addressable addressing systems, you need to adjust your calculation accordingly. But it is not that difficult, actually. It is just a different notation, that's all, from word to byte. Okay, then we have something called cache index. Okay, cache index is that cache line that you want to access, or line index, cache line index. Let's talk about that one. Cache line index. Let's call it I, which is your block address BA that you calculated already by A div K. Now it is BA, that would be mod C, whereas C is the total number of cache line that is available in the system, which is also predefined. Like each chip has is already predefined number of line in the cache, and it is in the definition of the system. So that's a constant. We calculate that cache line index. So this quantity specifically means that which line I'm going to access to see if the block is present or not. So maybe it is 3, this results in 3, for example. So you go there and see if it matches with the tag, and if it matches with the tag, then we know that block is present in the cache, and then we use this quantity block index to access that data within the block. Okay, maybe it is somewhere here in the block. So we access the data. If it is a word addressable system, it's a complete word, it's taken out. If it is a byte addressable system, byte is taken out, or it's depend on which load word, store word you are trying to use there. So really context dependent on what instruction you are operating on that specific address. Now, next, last but not the least term is the tag. Tag T is computed as, let's call it a T, your block address div C. So that's your tag. Okay. Now let's take an example. Okay, let's take a system which has, let's say, it's a word addressable system. Let's say, let me just describe that system. It's a word addressable system, and then it has, let's say, entire memory has 4 gig word, means practically we are talking about 4 gig addresses, 4 gig address. So 4 gig word size, so size is memory size, main memory size equal to 4 gig word. And then let's say block size is, let's say what, 4K word. Okay, 4K words. And number of cache line is, let's say, 1024. Okay, 1024, which is basically 2 to the power 10, right? 4K words, that means we are talking about how many words that it is, 2 to the power 12 words. That means we're talking about 2 to the power 12 words. Each block has that many words. Okay. And this is in terms of power of 2, it is 2 to the power, okay, 32. So 2 to the power 32 addresses are there. It's a word addressable system, so that's fine. Now let's say we are trying to access this address, maybe 0100 AB5. I just picked up a random number, okay, address to access. Now we need to see if that corresponding block is present in the cache or not. So that's the question for us, and let's see how we can manage it. First of all, you see it's a 32-bit address. So let's first try to make it a 32-bit in a binary. Okay, so this is hex number 0100, that address. So it becomes like this: 0000 0001 0000 0000, and A is 10. 10 is 1 010, B is 1011, E is 1110, 5 is 0101. So these are my all 32 bits here. And you see, since my block size is 4K word, 2 to the power 12, that means my block index is basically 12 bit, which is like, this is my block index. In fact, if you see, this is nothing but this address mod of this K, where K is block size, this one. Okay. And then that means the rest of the part, rest of this guy is my block index. Sorry, what am I saying? Block address. This is the block address. And this part, the other part was my block index. Since it is a power of 2, we can actually avoid the real calculation of modulus, and we can just pick up this 12 bit from the left hand side, and that's would be always the modulus of a mod of K in this problem. Now let's now deal with the BA, and we need to separate them into tag and cache line index I. So I would be cache lines. In the summer of cache line is 10, like 2 to the power 10. That means we need to yank out 10 bit out of it. We need to yank out 10 bit out of it. Wait a minute. 32, 10, 22, 10. Okay, 10 bit. Yeah. So which would be like 448. I think this part. This part maybe, let me just very clear, 448, 10. This part is your I, and rest is how much? Like rest is 32 bit minus 10 for index minus 12 for the block index. So this is like another 10 bit. So of course we can recheck. The rest of them are another 10 bit. And this is your tag T. This is your tag. So now that means here my tag is what? In terms of hex, if we want to write in the hex, it will be 4, right? Hex 4, that 10 bit represents that. And index would be, in terms of hex, it would be A. And block index would be very simple, right? BE5. So that system, what it will do, it will access the cache line A, which is 10th cache line. Let's say that cache line is somewhere here, right? Number 10. I have some tag, some control bit, and then entire block. So let's say this is number 10. So the system will go and access this cache line 10 and try to match this tag value with the stored tag value. So let's say that tag value stored was 4. Let's say it matched. So if it matched, then it will go and access this block index, maybe somewhere here, and retrieve the value and send it back to the processor. So that means it does not go, if your address you asked if it is present in the cache, it is not even go and query on the main memory. So that's why, since it is very fast memory, cache memory, it is sitting inside the processor. So it is a faster operation if the block is present in the cache. Corresponding block we are looking for is present in the cache. Question. So in the exam, if some problem like this given, that okay, given an access and I have this memory configuration, uh, let's say determine the tag index and block index, right? Cache line index and block index. So first you need to notice if the sizes are of power of 2. If those follows power of 2, you really don't need to go to the complicated calculation of modulus calculation, division calculation, all this stuff. You just split your bit pattern. You expand this address into 32-bit and or corresponding number of bit as problem says, and then split them up. Block index, cache line index, and tag. You just need to determine that. That's very simple problem actually.
And how will we know how wide they are?
How what?
How will we know their size?
That would be given in the problem.
Oh, okay.
Yep. Okay. Now let's move to the next problem or next discussion. It's kind of it's a reiteration of what we described in this lecture video, but I just want to make sure you guys got it. So in this problem, we start with let's say a sequence of block address. Okay, we don't know about the original address, what block index. We're not interested of that. We're just operating on the block address itself, which means like we already computed the block address. We know that, and that is being accessed in this scenario. And we want to see what are the dynamic situation happens. So in this problem, I get the block address as 5 bits, and I have 3 bit of cache line, like 8 cache line, 2 to the power 3, and it's represented by this bit pattern, 0 to 7 bit pattern, 3 bit. So each of them, we start with a blank memory, blank cache. Let's say this is a power up situation, and we see what would go on there. Okay, so we start with the very first one, block address, and we want to split up them into the cache line and tag. As we see that number of cache line is 2 to the power 3, that means our cache line index would be this 3 bit. So the tag would be this 2, right? So that's why we can directly compute the cache line index as 110 and tag as 10. Now we go and look now in this cache line 110. 110, we see that there is a valid bit which says no. That means there is no data yet. So that in that situation, it is a miss. And then what will happen, it will go and change, it will fetch the data from the main memory and 110, okay, and then fill out the entire data line, okay, fill out this entire thing, and then turn it to valid bit yes, and store a tag of 10, okay, and then access that corresponding index and return the data to the processor and so on. Now next operation, then we can similarly write down my cache line would be 010 and tag is 11. And we see, we go to that cache line 010, right? 010, and we see that there is that valid bit is not a valid bit, so that means that's a miss, and we need to bring up the data onto that cache line 010. So we bring up the data there and store the tag 11 there and make that is a valid bit. Now we move on to the next one where my tag is cache line is 110 and tag is 10, and let's see 110 110. Okay, that's a valid. So this one is a valid. Okay, 110 and tag actually match. Now this is the hit. So what will happen? Corresponding data will be accessed just from the cache and returned back to the processor. And the execution moves on to the next one. Next one, my cache line is 010 and tag is 11. So let's see what happens here. 010 valid and tag match. Voila. So that's a hit. That's a hit. And data is returned back. Then the next one would be cache line 000, tag as 10, valid bit no, that's a miss. And we need to bring the data into the memory from the main memory, from the cache, from the main memory to the cache memory. Add the tag 10, make it a valid bit, and now return the data. Now we move to the next operation and say that, okay, my cache line is 011, tag is 00. So let's see 011, 011, not a valid. So that must be a miss again. And then we bring the data back, change the valid bit, store the tag 0. Okay, moving on to the next one. This is cache line 000, tag 10. Now let's see, let's inspect 000. It's a valid and has tag, oh, tag matched 1010, tag is matched. So this is a match, that is a hit scenario, and we return back the data. On to the next one, it is 1001. So 010 would be my cache line, tag would be 10. So in that case, what would happen is 010. Okay, so this one valid, but tag does not match. So that's a miss scenario. That's a miss scenario. So what will happen? The new data will come into 010. New data will come into 010. It will override the old data, and then it will change the tag to 10 and then serve the data back to the processor. So in this situation, you see that one another observation to make here, if we want to make an hit rate, what is the hit rate? Hit rate would be, there are how many access? 1, 2, 3, 4, 5, 6, 8 access, and out of them, 4, 5 are miss and 3 hit. 3, 8, which is like very small, very low at this point. The reason of that being very low is that we started from the power up address. So 3 by 8, let me just put that. What is it? 3 by 8? It's almost like 37.5%. That's the heat rate. Very low. Because in the cache, we want to keep the heat rate like 80%, 90%, that in that range. But in this situation, since we started from the blank, from the power up address, nothing is there. Of course, the initial access will be all missed. That is the real situation. Like when you power up your machine, your laptop, your cache is all blank there. And initially you will have a lot of misses and data chunk will be brought into the cache from the main memory. Now, as the time progress, as your execution of the program progress, those heat rate will start gradually rising on. Because the heat rate, like if you just try to make a graph over time of the heat rate, it will start very low and ultimately at some point of time it will go and saturate at hopefully like around 80 to 90% of heat rate. Okay, so but initial this ramp up time, this is like from power up situation till it basically ramp it up the access, it will have a lot of misses at the initial start point. All right, question. No, not any questions. Okay. So now after this, in the next lecture, what we'll be learning is there are certain challenges around the write operation. Read operation is very simple. Data is there, not there. If not there, just bring it from the main memory. Now, what happens to the write operation? Like you want to write onto an address. Do you always write back to the main memory to make it a consistent content between the main memory and the cache blocks? That is the situation there. Remember, like theoretically, the block present in the cache has to be identical that is present in your main memory. So that poses some challenges for the write operation, and you cannot avoid write operation in your program execution. Any send program has writing into the memory. So now how do we handle the write situation? Do we want to keep the main memory and the cache always consistent with each other, or we can actually delay that consistency to later point of time? What would impact my performance better or worse? That kind of things that will be discussed in this next cache memory tree, that part. Okay, so I don't have any more thing to discuss tonight with you unless you have more questions for me.
Yeah, what's the use of the block index in the memory when we already have the address, the block address?
So remember, the block address is, let me share my screen once more. So block address, okay, block address is telling that which block you are going to access. And block index tells that within that block, which specific data you are going to access, right? So your entire block is in the cache line, right? It's in the cache line. So you must, okay, first of all, on the cache access, you know that your block is there in the cache. Now you need to know which part you need to access from that block, and that is your block index. So it is not really related to the ultimately to the target address. Like this a target address maybe belongs to this one or somewhere here. But what matters is this: you split this up into the block address, and then split that up into tag and the cache line index and check if that block of data present in your cache. Now, if it present in the cache, in that situation, you use the block index to access within that block and pick up the data from. Does it make sense, Yorick? Or did I answer your question?
Yes, sir. Thank you.
Okay.
And the tag was you use that to detect if that basically the processor can use that to detect if that's the specific memory block that they want to access, right? It's like a small sample of the data inside of the block.
Yeah, so processor does not incur much waiting time on that if the block is present in the cache. So this is all through the circuit, right? All through the electronic circuit, and it almost you can imagine it instantaneously determined if the block is there, and it can access the block almost instantaneously. Point become when it is not there and you need to bring it back the entire block from main memory into the cache. That's a time consuming operation. During that time, processor or any system has this option, like it depends on like how complicated you want to build your system, like as a hardware engineer. Do you want to just keep the processor wait till that block copy is done, or you actually want to switch the processor with some other processes to concurrently go and execute? Okay. And that's a very good question, Yurik. That actually will bring another concept of hardware threading. Remember the hardware threading we discussed in the parallel computing section?
Or you mean the strands?
Strands, exactly. Strands philosophy was this, like when we are waiting for that block to be copied onto the cache, let the other strand flow through. If that data is present in the cache, why to wait? We just keep using the processor instead of stalling it. So that's the whole philosophy. Okay. So
All right.
how for, yes, Yuri.
Oh, nothing. Thank you.
Okay. All right. How is the project coming up? You have less than a week to submit it. Why don't I just launch that poll and see? Like you can answer it anonymously and let's see where we are. 22 of 27, 5 more to go.
Hey, Professor, just a quick question.
Yes, Avijit.
Yeah, so we know that semester is gonna end around May 20th. I was just wondering, like, why is the due date for Project 3 so much earlier than that?
So one thing that I want you guys to concentrate on the theoretical study for the prepare for the exam. And secondly, then we have time for the TA and grader to grade your project. They're also students, they have their exam too. So I don't want to overload them during their exam.
Oh, okay. Thank you.
Okay, maybe I'll end the poll, share the results with you. Okay, I don't know what these 3% said haven't started yet. Tough time for you then. I don't know. Done with the task, 2 of them. 21 of you are falling behind. So maybe next couple of days you'll be busy in finishing the project. Please make sure you finish it, write the report, and be on time on these deadlines. Okay, next, I think 4th May. All right. Then if we don't have any other things to discuss, or if we don't have any other question, then we can stop tonight early. Go back and keep working on your project 3. I'll wait probably a minute or two to see if there are any more questions, then we'll stop this session.
Professor,
Yes, Laura.
is there like a PDF or something like a guide like for the same thing we have for project 2 for this project or not?
No, this is all your individual lab is your guide.
Only the labs. Okay.
Yeah, only the labs. Yeah, just follow through the labs.
Okay. Thank you.
And if you have any other question, just shoot me an email or put it on the discussion. Okay. Okay, then everybody, good night and see you on today's Thursday.